Hello everyone and welcome to this series on the STM32 and implementing real-time digital signal processing on it. So I'm going to cover the basics of the STM32 as well as some of the more advanced features like timers, ADC and DACs using DMA, most importantly interfacing with ARM's CMSys DSP library, as well as taking advantage of some of the hardware accelerators STMicro offers like the FMAC and the Cordic. However, before I begin with the STM32, let's start with something more familiar, the Arduino platform. So the Arduino is based off the 8-bit AVR microcontrollers produced by Atmel. It's really gained popularity due to its simplicity and easy to use IDE. However, it lacks capabilities that we're interested in for real-time digital signal processing. It has a very slow main processor clock frequency. It's got limited memory and I/O. It's got very simple ADCs that don't allow us to do any kind of high frequency sampling, and it lacks a debugger. So for real-time digital signal processing or control systems, this is not what we want to use. So the STM32, on the other hand, is what we want to use. So the STM32 refers to the family of 32-bit microcontrollers from STMicroelectronics. They come in a wide variety of shapes and sizes with a long list of different capabilities. Three of the most popular STM32s that you may have seen before is the Blue Pill, the Nucleo series, and the Discovery series, but more on these later. Okay, so before we start talking about the different families and series that STM32 has, let's talk about the naming convention. So the naming convention breaks down the name of the STM32 into a type, a core, a line, a pin count, a flash size, a package, and then a supported temperature range. So something like the Blue Pill is the STM32 F103C8T6. So F corresponds to the type, so it's a mainstream microcontroller. 1 is the core, so that's an ARM Cortex M3. 03 refers to the line. C is the number of pins, so 48 pins. 8 refers to the flash size. It's a 64 kilobyte flash. The package is T, so it's a leaded quad flat package. And then the temperature range is 6. So the chip is supported from -40 to 85 degrees Celsius. So there's more than a dozen different series within the STM32 families. So they have a wide range of capabilities. So each one of them is a 32-bit microcontroller. They come in clock speeds from 32 to 550 megahertz. For I/O, the different chips have packages anywhere from 32 to 144 pin packages. Flash memory, 16 kilobytes to 2 megabytes. SRAM, 2 kilobytes to 1 megabyte, and a plethora of different communications protocols. So STMicro breaks down all these different series into four main families. You have the high performance, mainstream, low power, and wireless. So the high performance family comes in with really high clock speeds and correspondingly high core mark scores, meaning they can crunch through a ton of instructions per second. They have large amounts of flash memory, and most of these have a floating point unit to speed up floating point operations. The highest performance line within this family is the H7 line. So the H7 features both single and dual core microcontrollers, and these can go up to 550 megahertz, which is crazy amounts of power for a small little chip. Next, we have the mainstream line. This is where the Blue Pill sits, the STM32 F1. This is what's most popular and what you can usually find on Amazon. Things like the F0, the F1, and the F3 within a Nucleo package. Although they're the mainstream line, they're usually far more capable than what you actually need, and it's what most projects should probably be built around. Next, we have the ultra-low power line. So these just draw very low amounts of current, say if you were doing something with a battery application. And then lastly, we have the wireless family. So these have built-in RF transceivers, making them capable of communicating over Bluetooth and LoRa and some of the other local wireless protocols that have really popped up for microcontrollers, as well as they also support like GFSK, GMSK, and BPSK. So you can do more than just that. You could build your own like SDR network if you so choose. So the STM32 chips are supported by a diverse ecosystem of hardware. So you have things like the Blue Pill, which are specific just to the F103 chips, and then you also have the Nucleo and the Discovery. These two series of boards, you can get almost all of the chips that STMicro creates on one of these platforms. The Nucleo in particular comes with 32, 64, and 144 pin variants, depending on how much I/O you need. The 64 and 144 pin variants also feature Arduino style headers. So if you have existing breakout or expansions for Arduino boards, you could use them there. The Discovery boards are usually for the more powerful chips like the H7 or the F7 lines. They come with extra features like on-board ADCs and DACs that are off the chip but still on the board and easy to use. They also might have things like microphones or external memory or audio jacks to take advantage of. And then there's also things like the eval modules, where these are for individual chips, and then they pack the eval module with tons of different features. So everything you could possibly think of: connectors, peripherals. This example here has a touchscreen on it. Everything that a developer might need, and in an easy to use way to test out a chip and its features. And then there's also expansion boards. So these are compatible with the Nucleo or Arduino pinouts. So say like you need an interface with motors, you can buy a motor driver board. If you need Bluetooth, you could buy a Bluetooth board. An easy way to essentially add functionality to the board that you have. So something to keep in mind about the STM32s is to actually communicate and be programmed by a computer. You need a programmer. So boards like the Blue Pill will require an external ST-Link programmer. You can easily find, say, an ST-Link V2 on Amazon and use that. On the other hand, boards like the Discovery and the Nucleo have on-board programmers. The Nucleo, funny enough, actually designs the board in such a way so that if you don't need the programmer anymore, you can snap the board in half and take off the part with the programmer. All right, so to circle back to the topic at hand, our goal was to take an STM32 and use it in a signal processing application. So we're going to be taking an analog signal, we're going to be sampling it with the onboard ADC, we're going to be doing some sort of mathematical processing to it, and then we're going to use a DAC to convert that digital signal back to an analog signal. So to perform real-time digital signal processing, we need a chip that's capable of sampling at high frequencies, doing math in real time, and then also converting that back into an analog signal at high frequencies. Fortunately for us, STMicro has a board just for this purpose, being the STM32G4, which is optimized for mixed signal applications, which is exactly what we're doing. So the STM32G4 being a mixed signal board, it comes with a pretty respectable processor speed of 170 megahertz. It's got good flash memory and a good SRAM size, but most importantly, it has a good mixed signal capability. So it comes with three 12-bit ADCs, which are capable of operating at 4 megasamples per second, so well above the Nyquist rate of most things that we're going to be doing, and then 4 12-bit DACs capable of 1 megasample per second. As well, it also has some stuff like comparators and op-amps, which we won't be using, but are nice to have if a future project does arise. Most importantly with the G4 is it has 2 math accelerators. So these are coprocessors that operate independently of the main processor. So it has a Cordic and an FMAC. So the Cordic speeds up trig functions, so something like taking a cotangent usually takes a while on a normal processor, but with the Cordic it's designed to mathematically speed up this in particular, so it will be very fast. As well as an FMAC, which stands for Filter Math Accelerator. So things like IAR and FIR filters, which normally would bog down our main processor, we could just unload those to the FMAC and have that run simultaneously while our main processor runs. And these aren't the only things that the G4 can do. If we look on STMicro's website, they give a long list that breaks down each one of the different capabilities and features, and it's definitely worth a look. So where's the best place to buy this? I would stay clear of Amazon. Amazon mostly just has the mainstream boards. You can't usually find anything particular, especially if you want something like a G4. It's not sold on Amazon. Instead, use places like DigiKey and Mouser, where you can sort for the actual chip that the board is on and then all of the different boards that they make around that chip. So we have our board picked out and we can buy it. What software are we going to use? Well, there's a few different commonly used pieces of software. We have the Arduino IDE, you have ARM Mbed, you have the ARM Kyle, and then you have the Cube IDE that STMicro provides. So a lot of people will start with something like the Arduino IDE, and it pulls people in because of its simplicity and easy to use. However, it really limits you on the actual features that you can use on your STM32. It kind of takes your STM32 and it removes all the capabilities and turns it into a basic Arduino. So we're going to stay clear of that. There's the ARM embed, which is kind of a middle ground between the Arduino and something like a full-blown microcontroller development environment like the Cube IDE, but it is popular and it's easy to use, but it still doesn't give you access to everything. So we're going to stay clear of that as well. There's the Kyle, which is an awesome piece of kit to use. It's ARM's premier microcontroller development kit, but it's expensive. And you can use the free and light editions, but they have some limitations on them that aren't worth dealing with. So for that reason, we're going to choose the Cube IDE, which is STMicro's development environment made for the STM32s. There's a bit of a steep learning curve to use it, but there's good resources available, and it's an incredibly powerful piece of kit. So that's the end of this introduction. So in the next video, I'll cover a blinking tutorial on getting started in the STM32 Cube IDE, and then we'll build from there and start building an actual DSP system to use on the STM32 G4. Stay tuned.